This course will cover the fundamentals of IO-Link. In this course, we'll give an introduction to IO-Link, its physical layer, and communication protocol. IO-Link is a standardized protocol regulating how sensors in industrial systems interact with a controller. Sensors and actuators have long been intelligent and capable of providing more than industrial systems have demanded of them. Until recently, there was no universal, efficient, and economical solution on how to best take advantage of those capabilities. In 2008, a group of 41 sensor and actuator manufacturers started the IO-Link consortium, which standardized the hardware, the physical layer, interface, and standardized communication, the data, protocol. Historically, a typical sensor consisted of the sensing element and some way to get the sensing data to a controller. Data was often transferred to the master or controller in analog format and was unidirectional, from the slave to the master only. This added extra steps. Note the D to A and A to D shown in this simple example, and added extra cost and extra footprint. This also was susceptible to noise, limiting the full functionality of the system. As technology advanced, sensor manufacturers found that they could integrate more functionality into their sensors, eliminating some of these problems. Binary sensors are created. They are defined and standardized in the IEC 60947-5-2 standard. The standard defines binary sensors as a sensing element, for example, inductive, capacitive, ultrasonic, photoelectric, etc., with a semiconductor switching element. Per the standard, switching elements can be defined as normally open, normally closed, changeover, or user programmable. Outputs can be configured as high-side switching, PNP, low-side switching, NPN, or push-pull. Binary sensors helped to solve the physical issues with sensor communication, but data was still limited to communication from the sensor to the master. However, sensors also had to be manually calibrated, and system errors and issues still required a technician's attention on the floor. The next step in sensor evolution is the IO-Link standard. IO-Link is officially known as the Single Drop Communication Interface, or SDCI. The IO-Link standard is IEC 61131-9. IO-Link sensors keep all of the best that binary sensors have to offer and add a bidirectional data line. The sensor can now send and receive information to or from the master. IO-Link masters provide both binary sensor, digital input, digital output, and IO-Link communication. This allows IO-Link to be added to an existing system easily. When combined with gateway capabilities, this system can then become a field bus I/O node. IO-Link functionality in a system reduces maintenance and increases uptime. The devices can be plug and play with parameter settings that can be downloaded from the controller. Customers no longer need a technician on the floor to do this. Machine downtime is no longer needed to reconfigure the devices. IO-Link allows for continuous diagnostics and improved data logging and error detection. And it's also an easy standardized installation with commonly used connectors and cable that allows direct binary sensor upgrades. IO-Link sensors now have configurable settings for the PNP, NPN, or push-pull that can be changed on the fly. The IO-Link standard states that IO-Link communications are limited to a distance of 20 meters using unshielded cables. IO-Link connectors are already in wide use in industrial systems. M5, M8, and M12 connectors are allowed. Typically, M8 and M12 connectors are most predominant. IO-Link communication is between one master and one device, a sensor or actuator. Communication is binary and half-duplex. Communication requires a three-wire interface: supply, data, and ground. The supply range in an IO-Link system is 20 to 30 volts for the master, 18 to 30 volts for the device, the sensor or actuator. Communication is with a 24-volt pulse modulation. IO-Link standardized connectors and cables are already commonly used in most industrial systems. IEC 61131-9 defines two types of ports, which depend on the type of connection and connector used. Port Class A have 4-wire connections as a maximum. They also support an IO-Link 3-wire connection system, which consists of signals called L+, L-, and C/Q. Some Class A ports may use a 4th wire, as shown for the M12-5 connector, which may be an additional signal line complying with the standard. Port Class A use M5, M8, and M12 connectors. Port Class B has 5-wire connections. These connections are for devices that require extra power from an independent 24-volt supply. Regardless of the port class, the C/Q connection is required for communication between the master and sensor. Although other inputs or outputs, digital input or digital output, may also be connected. Again, the supply range in an IO-Link system is 20 volts to 30 volts for the master, 18 to 30 volts for the device, whether it's a sensor or actuator. Here are some important numbers to remember. A rising IO-Link signal must go above 13 volts to be registered as a high. A falling IO-Link signal must go below 8 volts to be registered as a low. Note that the high and low detection time, TH and TL in the timing diagram, are 1/16 of a bit at least, and TND is the noise suppression duration, and that must be less than 1/16 of a bit. Industrial environments are harsh and require some special considerations to ensure that IO-Link devices and masters can operate in those conditions. The IO-Link standard sets a minimum EMC, or electromagnetic compatibility, performance requirement to ensure that IO-Link devices can withstand some common transient issues. For example, ESD requires plus or minus 8 kilovolts for air discharge, or 4 kilovolts, plus or minus 4 kilovolts, for contact discharge, based on the IEC 61000-4-2 standard. IO-Link communication is either cyclic or deterministic, or acyclic. Cyclic data typically involves normal operation. For example, the sensor sending data to the master. Deterministic data can take one of two forms. The first is configuration or maintenance information. For example, the master may configure the device after power-up, or request the device configuration right before it powers down. The second is event-triggered. Events are reported with 3 levels of severity: notifications, warnings, and errors. For example, when a fault or error is triggered. All communication between the master and a device begins with a request from the master. A device must answer all master requests. The sum of this back and forth communication is called an M sequence. It stands for message sequence. M sequences can take many different forms and vary in total length. Although M-sequence communication may vary, all communication between a port and a device takes place on a fixed schedule. When a master wants to configure a device or to communicate with it for the first time, it will send a wake-up request. A wake-up request starts with a current pulse induced by the master for the wake-up period. A wake-up period is typically 80 microseconds. The master sources or sinks the current to generate the wake-up pulse. If the line is low, the master will source current to pull it high. If the line is high, the master will sink current to pull it low. This wake-up pulse is detected by the sensor, either by monitoring the current on the line or by detecting a voltage change, a short low to high or high to low. When the wake-up request is received, the sensor must configure itself in receive mode. The response must be within 500 microseconds of receiving the request, or an error will be generated in the master. Once the device has been set to receive mode, the master then starts to learn more about it. The master sends multiple messages at the COM3, COM2, and COM1 data rates, that's fastest to slowest, and waits for the device to respond after each send. Any given device is required to support only one of the COM1, COM2, or COM3 data rates. The device will respond at its rated data rate. When the device responds, the master is then able to communicate with the device. The master also reports the device and its COM rate to the system management. The master can retry the wake-up sequence a maximum of 2 times to establish IO-Link communication. If the wake-up request fails, and then fails a second time, the device must set the CQ line to SIO, digital input or digital output binary sensor, mode. All IO-Link devices, sensors or actuators, must have an IO-Link device descriptor file, called an IODD, available to customers. The IODD contains all necessary properties to establish communication, device parameters, identification information, process and diagnostic information, an image of the device, and the manufacturer's logo. IODD files are XML files. The structure of the IODD is outlined in a separate document from the IEC 61131-9 standard. This is called the IO-Link device description. Industrial sensors, like many technologies these days, are trying to pack a bigger punch in a smaller package. This slide shows a number of examples, such as a photoelectric sensor, inductive proximity sensor, magnetic sensor, a safety light curtain, and a pressure sensor. To date, Maxim has 6 IO-Link reference designs, including an ambient light sensor, an optical proximity sensor, a digital input hub, a servo driver, an RTD temperature sensor, and an IO-Link master. This is an example of a 300 milliamp IO-Link master transceiver, the MAX 14824.